Just did a video, or I just streamed, I should say, on what I've been calling sizing computations in Hypergeometrica, and I thought it was a disaster. I don't know, it was not good. I didn't get anywhere really, and I fumbled around, and it was just not good. I was attempting to do some things which I'll recap here, and I'm probably going to repeat myself a little bit, but hopefully it'll be a little cleaner this time. I just ate bacon, and I just solved all the world's problems, and so I think this video might be a little bit better. Alright, let me grab my stuff. I'm going to try to do more coding in this one too. Last time I spent a huge amount of time not coding. Alright, so this is gonna be a little bit of a pain to repeat, but I'll do it anyway. Fourier transforms. I'm gonna recap again, a recap of a recap. Normal Fourier transform is something like this, 2 pi, this is acting a little weird, 2 pi I, screw it, let me just erase it. Alright, where is it? 2, this tab was super annoying. 2 pi I, if this is indexed in k, then it's j k over n. Here, n is our transform length. We have f capital J, which is transforming lowercase f j. This is our root of unity. All of these exponentials right here fall on the unit circle. That's a horrible unit circle. So horrible that I feel like I need to do a little bit better. That was also bad, but you get the point. Anyway, all these fall on unit circle and evenly spaced intervals. Mostly this k over n term determines that, and that's raised to j. So we can actually rewrite this as k e to the 2 pi I k over n to the power of j f of j. This is a common theme if we generalize this and kind of say that this thing is omega k sub k, then we can rewrite this as equal to omega sub k to the power of j f j. So the whole idea of the number theoretic transform, as I talked about in one of the previous videos, is that instead of wk being an element of the complex numbers, we instead choose a wk that's an element of some ring with a particular invertible element, namely one that isn't susceptible to round off error. And such a thing is the integers mod m. So if we have a modulus m, then if I draw this out, z over m z. And so we can compute such these things. And the formula is the same. It turns out that if omega is a primitive root of unity, then this is transformed in much the same way, where we can write omega k j f sub j. So I talked about all that, and the big point in choosing this over this was the following. When we do computations in C, in the complex domain, on a computer, a complex number z equals a plus bi is represented as two double floats, basically. So this is a double, and as is this. So in memory, it looks something like this. This is 8 bytes, and this is 8 bytes as well. And the first double float is here, the second double float is here. The big point is that this is a finite representation. The complex numbers are uncountable, even the rational numbers are uncountable, and so the total number of possibilities to fill up 128 bits is limited. There are only a limited set of complex numbers, and as such, when we start doing transforms with them, complex fast Fourier transforms, you're going to get round-off error. There's going to be, at some point, if we add two numbers z1 plus z2, or multiply them z1 times z2, the product z3 is necessarily going to be an approximation of the true sum. And since every operation produces an approximation, for the most part, it adds up. So this isn't really a problem when our transforms are not very long. If they're very short transforms, then it usually doesn't lead to problems. There's one case where a mathematician was computing pi out to something like 50 million digits, but after the first 20 million, everything was wrong. And the reason is because for transforms of that length and the fast Fourier transform that he used, all of those minuscule, this is, like I said, z1, z2 equals the true z3 plus some error. This error grew large enough such that when they did a convolution, the convolution was an incorrect result. So only about 20 million of them were correct. So the whole point of this is that if we move to something that's discrete and finite, like integers mod m, then there's no error right here. If we multiply two integers, a plus b, or sorry, a times b, mod m, the result is exact. So this is an exact result. Let me make sure that this window let's also do this. So that's the whole point of going from complex numbers to these integers mod m. The problem that arises is, let's close that. One problem that arises is if we're still doing integers, if we're doing multiplication of multiple precision digits, then we can still get a different type of problem, which is products, for example, might overflow. So let's erase some of this. And here's the crucial point where I really went off the deep end in my last stream, which I am aiming to correct here. So let's erase this. When we convolve two sequences, so a little backup, major multiplication of numbers. If we have a number like 1, 2, 3, and we multiply it by 4, 5, 6, the way to do this multiplication is to put the digits into an array and double the length. So the result of 1, 2, 3, if you have two n-digit numbers, or if you have an n-digit number and an m-digit number, then the resulting number is going to be n plus m. This can really be seen if you have a number n then the number of digits is equal to about log n, something like that. It's on the order of log n. So if we have a number a with log a digits, and we have a number b with log b digits, then a times b is going to have log a b digits, which is equal to log of a plus log of b. It's a plus right here. But this is just the number of digits in A, and this is number in B. So, since we get the sum, if we're multiplying two n-digit numbers, like 1, 2, 3, 4, 5, 6, then the result could be of length 3, 4, 5, or of length 6, because this is 3 digits, this is 3 digits, so the result is going to be about 6 digits, plus or minus a couple. It's actually plus or minus 1, I think. I think it's actually either 0 or minus 1. So what we do when we do this multiplication, if we had a billion digits or whatever, we put these into an array. 1, 2, 3. And then we pad it with the number of digits that are going to be in our result. So we need 3 more to have 6 digits total. And then what we do for our second number is the same. 4, 5, 6, 0, 0, 0. So let's call this sequence capital X, and let's call this sequence capital Y. Then our result is going to be X times Y, obviously, equals the result, which is going to be, let's actually do this. Times 1, 2, 3, 4, 5, 6. Whoops. 5, 6, 0, 8, 8. So this is going to be, where is it? Sometimes I have a hard time finding the cursor. So this is 5, 6, 0, 8, 8, and then we have this extra 0 right here, which is 0. In order to get that, what we do is we use the convolution theorem. The convolution theorem says that and this can go either way. Convolution in the time domain is multiplication in the frequency domain. So if we have x convolved with y, this is the same thing as, or if we do the Fourier transform of that, Fourier transform x convolved with y, this is the same thing as the Fourier transform of x pointways multiplied with y. So one little point, it might seem confusing that I talked about multiplication here and here. The first multiplication up here, let me move my hand a little bit. This is pointwise. This is more akin to convolution right here. The reason is, if we want to compute x times y, we don't just do 1 times 4 and get the result. We don't do 2 times 5 to get the result, and so on. What we have to do is take this number and multiply it by every single number here. Then we take this number and multiply it by every single number. And then once we do those, then we add them all together, we do a bunch of pluses, and then we get this result down here. That's very much like convolution. So what this is saying is that if our numbers are sequences of digits, then this is kind of